Hello, everybody. Today, we're talking about dynamic games with complete information. For these examples, we'll talk about two-player games that are simultaneous move. The general format/timing of these games is that the first player makes a move/chooses an action from a list of actions. Player 2 then makes the move after player 1 moves, knowing the move of player 1. Unlike static games with complete information, dynamic games with complete information can be represented with a game tree. This is because the moves don't happen simultaneously or at the same time. So, an example of such a game that we're going to go over today is called the trust game. During this game, the first player plays trust or not trust. Then, if the first player plays trust, the second player then gets to move. They choose to play honor or betray. If the first player chose not trust, the game ends there. This is the game tree for that game. So here you can see first player 1 goes. If they choose not trust, both players get 0. In here, the format, as normally it is with game theory, the first number represents player 1 and the second number represents player 2. Over here and in all the videos, I've color-coded it so blue represents player 1 and red represents player 2. So again, player 1 chooses trust or not trust. If they choose not trust, it's 0-0. Both players get no money and lead the game. If player 1 chooses to trust player 2, then both players get $1. If player 2 chooses to betray player 1, then player 1 loses $1, player 2 gains $2. This game, as well as being able to be represented with a game tree, can also be represented with a matrix. This is what such a matrix would look like. Here you can see player 1 at the top, player 2 at the top, player 1 on the side. Again, if player 1 plays not trust, then in both cases it's 0-0 for both the players. If player 1 plays trust, then the two scenarios, if player 2 chooses to honor or betray player 1. This is a different kind of problem from before, so we can't use the same methods and just compare the matrix. To solve this problem, we will use new concepts, backwards induction and subgame perfect equilibrium, which is what we're trying to find. So, to solve this, we start at the bottom. I will be using the game tree to provide a more visual aspect. So, like I said, we start at the bottom. At the very bottom, player 2 has the option to honor player 1 or betray player 1. What choice will player 2 make? Since 2 is greater than 1, player 2 will choose to betray player 1 because player 2 is acting in their best interests. Knowing that player 2 will betray player 1, what will player 1 do? So now this is what the game tree looks like. Player 2 honoring player 1 isn't an option anymore, so I've taken that off the game tree. So now player 1 has the option to play not trust, in which they'll gain $0, or play trust, in which the outcome is that they will lose $1. Since 0 is greater than -1, player 1 will choose to not trust player 2. By breaking up this game into smaller subgames and starting at the bottom, we were able to solve this problem and find the subgame perfect equilibrium. To illustrate backwards induction, I'll use another example to show how starting at the bottom, working up to the top, works for dynamic games with complete information. The reason this works is that if we were to start at the very top of the game tree, over here, and just figure out player 1 to trust or not trust, it'll get very difficult. We don't know what'll happen until we know the outcome of each of the moves. So, by determining what player 1 will play, we know the outcome of player 1 playing trust. That's why we start at the bottom. So, here's another game. Player 1 chooses yes or no, then player 2 chooses A or B. Here you can see the outcomes of each of the plays. So, again, we start at the bottom. If player 1 chose yes, then what will player 2 choose? Player 2 in this case will choose A because 4 is greater than 1. If player 1 chose no, and we arrived here at the bottom, then what will player 2 play? Since 5 is greater than 2, player 2 will choose A. So this is now what our tree looks like. Now, What will player 1 choose? Will player 1 choose yes, leading to the outcome of 2? Or will player 1 choose no, leading to the outcome of 1? Since 2 is greater than 1, player 1 will choose yes in this case. This is what the final outcome looks like. Now we have found subgame perfect equilibrium. Thank you so much for watching this video. I hope you liked it, and I hope it made finding subgame perfect equilibrium more clear for all of you.